Very good morning students. Welcome back to second year physics. In the previous actually we did about a Lenzilla. On the basis of Lenzilla, I will tell you one application. Suppose there is a one condition given, applications of Lenzilla. So there is a coil and there is a magnet. Both are at rest, north and south. See, coil at rest and this one also at rest. If the magnet is rotated like this, so try to understand, if the magnet is rotated, so that is there any current is induces? No, there will be no induced current. That is I is 0, induced is 0, because there is no change in flux. No, there is no change in magnetic flux. It is flux is linked, but there will be no change in magnetic flux when it is rotated. Just it is rotated like this. So when it is to be rotated, there will be no change in flux linked with the coil. When there is no change in flux is linked with the coil, therefore current is 0. This is one application. That I want to say second application. Suppose you take a coil, magnetic coil, one coil. See, the coil is held in the horizontal position. The coil is held in the horizontal position, and above the horizontal coil, if a magnet is allowed to fall freely, therefore what happens? See, if magnet is allowed to fall freely through the horizontal circle, like it is a one coil. When there is a magnet is allowed to fall freely, like north south, which is falling freely. When north is coming towards a coil, no, therefore the coil is behave like a north. Therefore when it is opposes the motion of a magnet, because it is faces the north, no, north lines is flows through the coil, like therefore the coil behave like a north. Then also magnet is false, of course, but there is a resistive force is acting, no? And you remember, there will be acceleration is greater less than the acceleration due to gravity. Acceleration of the magnet is less than the acceleration due to gravity. Therefore the magnet is falls freely, and the weight of the magnet mg is acting down. There will be a resistive force is acting, because the coil is facing a north, no, there will be a resistive force, or we can say frictional force is acting up, but then also resultant is act downward only, because the magnet is moving through the coil, it is falls freely. Therefore the resultant force Fr is equal to mg minus the resistive force. Shall I? Of course, because the resistive force is equal to what it is, which is the opposition offered by the coil, which is acting vertically up. But we know Fr is nothing but a magnet is moving with a Ma, no, then Ma is equal to mg minus F. So frictional force or opposition force will be, we can say like this. There will be opposition is like this. Therefore the from here also we can write acceleration of the magnet is g minus F by m, because mu take this side, mm will cancel. Therefore g minus F by a, when magnet is allowed to fall freely, and here after crossing the coil, sir, what will happen again? See, when the magnet is crossing the coil, no, there also what happens again? See, the coil is faces the south, right, north and south. Now the coil is moving away from, no, then there will be a, in this case what happens, there is an anti-clock, no, then it is attracts towards. Therefore the weight of the magnet mg is acting down. There will be a resistive force is acting again, which is acting up, because which attracts, no, it is a facing north and it is a south, no, both will be attracts. Therefore the resultant is again acting down only Fr. In this also same, then the net will be, we can say F net is equal to mg minus F. So like this, the one application related to the Lenzilla application, it is to be, you remember, suppose it is falling freely, no, for a freely falling S is equal to ut plus half at square. Of course we know u is nothing but a 0, because the magnet is falling freely. S is equal to 1 by 2 at square. So we know yes, you substitute here, we will get the another expression related to the distance travelled by the magnet. So it is about what we can say related to acceleration of a magnet, which is held in a position of horizontal circle. So this is one application related to Lenzilla. Of course we have different applications are there, but it is not required. That all related to what we can say about a NEET and JEE mains, right? Now let us, we'll move to the next one. about a motional EMF. Side heading as you take as motional EMF. Sir, what is motional EMF? This is for 4 marks question. And you remember in this chapter there is no deletions. We need to read all and we need to do all, right? So the motional EMF is nothing but a, say let us you take a one wire which is bent in the form of a U shape, like a rectangular frame. So that the wire which is bent in the form of a rectangular frame like this. So length of the wire is you say L and breadth is B you take. Okay. Now come to the point is there will be a, in this length is L and there is a one movable wire is there. The wire of movable it is which is moves freely on this rectangular frame. That mean here you take a like a rectangular frame. See for this rectangular frame there is a one wire which can move freely or which can slide over the rectangular frame. And this coil is placed in the uniform magnetic field. The field is which is cross. What is mean by cross? Yes, when you remember cross is nothing but a which is acting into the plane of a paper. That means this is produces because of the current carrying a conductor which is in the inward direction. There it is to be this field is produces. Now let us I want to say the coil of length I mean to say this rod or a wire of length is L. Now it is moving in a given a field. When the coil is moving or the length of the wire is moving in the field through a distance you say, through a distance suppose you say it is moved through a distance. See from this place to it is moved through a distance is dx. Length of the wire is you say L and which is moving with a speed is V. When it is moving in a given a field, therefore there it is to be EMF is induces because there is a change in field or the change in flux because of the coil is moving in a given a field. So that when coil is moving in a given a field, there it is to be EMF is induces. That EMF, induced EMF which we can call as the motional EMF. See because the coil is moving, the coil moving in the given a field, there it is to be what happens, EMF is induces. The induced EMF which we can call motional EMF. Now let us the motional EMF we need to find. Before that area of the coil is nothing but a L into dx. Shall I write like this? Length into breadth, because this we can say the rod or a wire is moved through a distance dx, then you say breadth it is and the length is L. So area will be like this. Now we need to find a motional EMF. E is equal to, it is a d phi by dt, of course, simple it is, but phi is nothing but a BA it is. So E is equal to d by dt of it is BA it is. Here you write B is common, d by dt of, here L is nothing, A you write, then EMF is equal to B into d by dt into length into dx. So E is equal to BL into d by dt into dx. You write as some, as you take as a distance. So dx instead of dx you write as a sx. ds by dt is nothing but a rate of change of position, is nothing but a velocity or speed. Clear? And therefore what happens? It is E is equal to BLV. Of course, it is a negative rate of change of flux, everywhere you write as minus. So this EMF is nothing but a BLV. EMF induced in the in a given a field if the rod or a wire is moving through a distance is dx. Therefore there is a EMF induced in the conductor or a given a wire is equal to E is equal to minus BLVE. B is nothing but a magnetic field, L is nothing but a, we can say, length of the wire, V is nothing but a speed. Therefore, we can also write like this in terms of cross product B into L cross V, of course. BLV sin theta we can say, or we can say L cross B, no, or we can also write in terms of E is equal to L into V cross B. Yes, we can it is like this. We can also write in terms of B into L cross into V. These all are right answers only. There will be a EMF is induces because of the wire moving through the given a uniform magnetic field. Okay, this is the related to about a motional EMF. Sir, when conductor is moving in a given a magnetic field, so there will be the conductor behave like a EMF of a cell, because in this conductor there is a EMF induced, no, that EMF is nothing but there is a current flow. That mean here I will show you another diagram. Same conductor you take as like this, which is placed in the given a field, right? There will be a both, because the current is moving, nothing but a what EMF is induced, no, EMF induced nothing but a what happens, this conductor of a and B, you say, below the conductor it behave like a negatively charged, and above we can say positively charged. Of course, inside the conductor, because it is behave like a EMF of a cell, no, inside the conductor there will be a current flow from the negative to positive, because it is behave like a EMF of a cell, which one, this conductor which is moving in the uniform magnetic field. Therefore, the conductor is behave like a EMF of a cell, EMF of the cell, it is behave like a EMF of a cell. So inside the conductor or inside the wire, it behave, or the current direction which flows from negative to positive, inside it is like behave like a EMF of a cell, no. There it is to be what happens here, it is the magnetic induction force is induces at the bottom, and there will be, it is to be induces FE, electrical field intensity is induces, because both electric and magnetic field is creates, no. There it is to be what happens, it is behave like a positive is one more is, you say, it is a AB, no, here it is you say VB is the potential difference, VA is the another potential difference. So there will be a what happens, we can say always VB is greater than VA it is, because it is a positive, no, higher potential it is VB minus VA we can say, because there will be a magnetic induction is produced, no, so that we can say according to that VB minus VA is equal to BLV, which is nothing but a VB minus VE is nothing but a EMF of a given a cell. So that's what we can say when a conductor is moving in a uniform magnetic field. Therefore, in that conductor there it is to be current flow inside the conductor is from negative to positive inside the conductor. That means that conductor is behave like a EMF of a cell. That's what I mean to say. A conductor is behave like a EMF of a cell. It is a one application, or it is related to this emotional EMF. We can take like this. Clear? Is it okay now? Now, come to the point is, in this again we have also some other also is there related to this, because when now the rod act as a EMF of a cell, no, inside the cell the direction of a current is from the negative to positive terminal. Is it correct? Yes. And here we can also say by using this Fe is equal to Fm, we can take, no, Fe is equal to Fm, electrical force is equal to magnetic force, electrical force is equal to magnetic force. So electrical force we know Vq is equal to magnetic force also we know BVq, so that is cancel, E is equal to BV. From this V is equal to E by B. Of course we know it is about a velocity selector. In case of a moving charge and magnetism, we did this one related to what? It is about a motional EMF, or we can say velocity selector. V is equal to E by B. E is nothing but a electrical field intensity, B is nothing but a magnetic field intensity, right? Is it okay now? Now, on this basis again we have some applications also, we'll see. Right. So there is one application. See, when the resistance of the rod is capital R, first application you say, the given rod resistance is capital R, you say. Therefore, is asking what now? Find a current. Induced current is asking. Induced current is asking, that is I. But I is equal to, we know, E by R, no? But E is equal to BLV, right? I is equal to BLV by R. It is, we can say, induced current. We can say it is what? Induced current it is. When the rod is moving in a uniform magnetic field. And also asking, see, a force acting on the conductor, because there will be a force is nothing but a BIL. We know I is nothing but a BLV by R. So it is B into your BLV by capital R into L. Therefore, B into B square, L square, V by capital R it is. Force acting on the conductor. When it is moving in a uniform magnetic field, not only that, we can also find a power. Power, it is, we can say, applied, or we can say power disappeared. Power applied or power disappeared. So power is equal to, that is, we can say, P is equal to F into V. Power it is. Power on the conductor, power on the current carrying a conductor which is placed in a uniform magnetic field. Power is equal to F, you know, B square, L square, V by capital R into V. Therefore, power is equal to B square, L square, V square by R. So these are relations related to the motional EMF. Motional EMF, when a conductor is carrying a current which is placed in the uniform magnetic field, there will be motional EMF and induced current and a force acting on the conductor, and the power appeared or power disappeared. We can say power is, we can say like this. So that these are what related to what we can say about a motional EMF. Clear? So you go through this motional EMF, because which is given in our material as 4 marks, and the question is very, very important. I'll tell you the page number also. Suppose you see the question. Yeah, page number 268, page number. Question number is 1, which is very, very important, 4 marks. So recently this question was given in the IPE, so that you need to read this question, and which are very, very important, right? And also Lenz'S, we finished in the last class. Lenz'S also important, because this was given in the last year, 2019, this question was given. Okay, as well as the define a magnetic flux. What did the experiment of Faraday's and Henry laws, that is Lenz's law, Henry laws, Henry shows, right? So these you read and you finish it, these questions from this questions of motional EMF. Clear? Right. So this is about today's class, and we'll see in the next class. Thank you very much.